Congratulations, you've survived one more chapter of geometry. Now, of course, it's time for a review. Let's work a few problems and see if we learned anything. Teacher has the pennants shown below. Which pennants can you prove are congruent? Well, let's see here. We've got two angles that are congruent, which means we know now this is an isosceles triangle. So these two sides are congruent, but that's about all we know. What about this here? Okay, this angle is congruent to this angle. This side is congruent to this side. This side is congruent to this side. So these two are definitely congruent. This one, well, we have two angles that are the same here and one side in between. In other words, this angle is congruent to this angle. This angle is congruent to this angle and this side. So by ASA, angle side angle, we know that these two are congruent, and by angle angle side we know that these two are congruent. So all three of these are congruent. This, well, gee, this is congruent to this, this is congruent to this, but all we know is we have two congruent angles. We need to know something about the length of one of these sides, and we don't. So I would say the hawks, cyclones, and bobcats could be proven to be congruent. I've never seen a team called the Cyclone. Most of the others look familiar. There's about 100. Oh, that's not true. There must be thousands of high schools called Hawks. It's one of the most popular names around. Anyway, I think B would be the answer. Hawks, cyclones, and bobcats. These three I could prove that they are congruent. This one, we need to know something about the length of at least one of these sides. In fact, any one of these sides, if we knew it was congruent to one of the others, we'd be cool, because we've got two angles that are congruent. But we don't have information on the sides, so it's only the other three that we can show are congruent. Now, here's a nice, simple vocabulary question. All they want to know is, what type of triangle? How would you classify this? Scalene Isosceles, right. Well, since they labeled these grids for us, it looks to me like 2 is right here, and 1, we might actually have enough information. For instance, this is where x equals 1, 2, 3, 4, minus 4. And this over here, let's see here, this would be where x equals 5. So this has a length of 9. We can figure that out. Now, if these two were equal, we'd have isosceles. I think you can tell from looking at it, it's not equilateral. And that's not one of the choices anyway. Could it be a right triangle? Yeah, that's possible too. So that could be a right angle. So what we need to do is put in some points here and make a definite determination. So if I label the points, first thing we can do is check the slopes. That's a quick, easy check. And if these turn out to be perpendicular, we're done, because we can choose right angle. So let's take the slope from here to here and see what happens. And how do we do that? Remember, rise over run. So I guess we can start here. We'll try 3 minus a minus 1 over 3 minus 5. And that's 4 minus 1 is 3 plus 1, 3 minus 5 is minus 2. So that's a minus 2. That's actually a minus sign there, not a dot. Well, what about the slope from here to here? Well, let's see, 3 minus a minus 1. Okay. Over 3 minus a minus 4. And that'll give us, 4 over 7. Too bad. If it was 4 over 8, we'd have something. It'd be the negative inverse, and they would in fact be perpendicular. But unless I made a mistake, they're not quite perpendicular, even though they look like they almost are. So, no go. That leaves isosceles if this leg is the same as this one. So now we have to check that. That's okay. We're going to use, notice there's kind of a similarity in the expressions you use when you're computing the slope and the distance. The difference in the y-coordinates divided by the difference in the x-coordinates, that's the slope. Whereas the difference in the y-coordinates squared plus the difference in the x-coordinates squared, you take the square root of that, and you get the distance. So you're actually using similar expressions. So let's do it. We got 3 minus a minus 4 squared plus 3 minus a minus 1. Squared. And if we take the square root of that, we'll get the distance. And what is all that? Well, that's 3 minus 4 is 7. Squared is 49. Plus 4 squared is 16. We want the square root of that. Well, too bad. We get 49 plus 16 is 65. And if it was 64, the square root would be 8, which still isn't 9. The point is, if we got the square root of 81, we'd know that this was isosceles. If this number in here is anything other than 81, we don't even have to really figure out what it is. It's close. This whole thing is just a tiny bit over 8. It doesn't matter. The point is, it's not equal to 9. That's all that matters. So, they look kind of isosceles, but they aren't. It kind of looks like a right triangle, but it's not. Scalene. The only other type left was equilateral, and it sure doesn't look like that. So I think they were, this is the kind of problem where they try to mess you up. It's really easy to glance at it and quickly say, oh, it looks like a right triangle, and grab that answer. Or look at these two sides, how they look about equal, and grab that answer, when in fact this was the correct answer, which had to do a little bit of calculating to make sure that we had it right. Here's one where we use the same triangle we had before, and they want to know which one of these points would produce a congruent triangle from this. And P and N is going to be part of our new triangle. We already have M and P. We just have to figure out where to put Q. Well, triangles are congruent to themselves, so I guess if this was Q, we'd be done. But that's probably not the right answer. Now, if this has to be one side, it seems like Q is probably going to be out here somewhere. Otherwise, this would be a side, but QMP isn't the one that we're looking for, it's QPN. So it looks to me like Q is going to have to be out here. Now, what's the x coordinate here? I think we already figured out was 1, 2, 3, 4, 5. Well, every one of these is less than 5 except this one. So if I was in a hurry, my first guess would be 12, 3 out here. It's, gee, I don't know. Be right about out here somewhere, right? And it looks to me like that works. Look at the other ones. I mean, if one of these is going to work, it's definitely not going to be, I don't think, 0 minus 3. Geez, that's way down here. Although, well, okay. We don't really know for sure that we couldn't go like that and produce another congruent triangle, do we? There, and then we'd have one. Darn, I was hoping we had a really easy way to do this. Doesn't look like it. Well, I guess we'll just have to do a little bit of work. That's tough, isn't it? I went ahead and drew in the possibilities just for fun. Here's the original triangle here. Okay. Now, if A is I think it's maybe slightly less confusing if I draw the coordinates in here. I use different colors so you can try to keep track of which triangle we're talking about here. If Q were 0 minus 3, that would put it down here, and that would be this triangle. If Q was minus 6, 3, then that would be this triangle. Here. This NP is a common side to all 4 triangles. If we had 12, 3, get this one here, and the last one is 3 minus 5. Well, this would be about the last one I would check. It doesn't look right to me. This one isn't too bad. But notice our original had one side equal to 9. This has a side equal to 9. It goes from 3 to 12. And this one goes from 3 to minus 6. This is where I would start looking. One of these two is probably the right one. Now, the way I see it, this side is shorter than this side. But it looks to me like this side here is longer than this side of length 9. This side has length 9 on our original. If this side is shorter, then our congruent triangle is going to have one side of length 9 and another one shorter. This has one side of length 9, but it looks to me like this is way longer than this side here. So I'm going back to checking this one. If this turns out to be the same length as this one here, well, now we got something, don't we? So let's check it. First thing we have to do is figure out what's the length here. This one we don't have to worry about. This is always congruent to itself. This side is common to both triangles. So if we can show that, and we already have that this side is equal to this side. So, in fact, I can draw a little hash mark in there if we want. There we go. All we have to do is figure out if this side is congruent to this side. Then we have side, 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 and the two triangles are congruent. That means what we have to do is compute this distance. For that, we need to know what point we're at here. Well, let's see. This looks like the point 3,3, I think. And this is the point minus 4. Yeah. Minus 4 minus 1. And this is the point 1, 2, 3, 4, 5 minus 1. If this diagram seems cluttered, that's only because it is. To get this distance here, we'll use our distance formula. Got a little more room here. There we go. We'll have 3 minus a minus 4. That's the difference in our x-coordinates squared, plus the difference in our y-coordinates, 3 minus a minus 1 squared. And that's going to be the square root of 49 plus 4. Pardon me, it's supposed to go like that. There we go. 49 plus, and that's 16, not 4. Jeepers. 4 squared. Okay. Well, we're back to the square root of 65. This one here, well, let's try it. We get 12 minus 5 squared plus 3 minus a minus 1 squared. Well, I think we're looking good here. We got 7 squared plus 4 squared. Square root of 65. They're equal. Okay, cool. That means that's equal to that. And it turned out it was this one. The quickest way to spot it was to look for, well, you saw what I did. I recognized that both of these had a side equal to 9, but this one looked like it was going to be way too long to match up with the other one. But yeah, it was kind of problem that takes a little bit of time. That's one thing you'll notice about standardized tests. There will be problems that you'll just fly through. You'll do them in seconds. And others that'll look kind of easy. You'll first glance at it, and then there's some work, and there's a little more work, and there's a little more. And before you know it, you spend a ton of time on one problem. That's a standardized test for you. What can you do? Here we have, well, they say it's an origami butterfly. I'll take their word for it. I've never seen one. What we need to do is find x and y. They've told us these polygons, which happen to be a quadrilateral, are congruent. We've mostly worked with congruent triangles, but if all the sides are congruent and all the angles are congruent, then the two polygons are congruent. It's the same definition whether you're dealing with triangles or quadrilaterals, any polygon. So this looks like a job for our, remember this, CP, CTC, corresponding parts, except in this case it's not triangles, it's a polygon. It's the same idea though. The corresponding parts of congruent objects are congruent. In this case, the quadrilaterals. All we have to do is spot the corresponding parts. It doesn't look too tough. It looks to me like this corresponds to this. So, we just need to match up our angles and set up our algebraic equations. For instance, here and here. These correspond, so we could write x plus 2y equals 106. And over here, we write x minus 11 equals 45. Now this directly leads to x equals 56. Just add 11 to both sides. we substitute that back in here. And we get that 56 plus 2y equals 106. Block this off. It's going to get messy otherwise. So I subtract 56 from each side, and I get 2y equals 50, or, of course, y equals 25. Does that make sense? Well, we already know x minus 11 is going to be 45, so it certainly makes sense over here. What about 2y is 50, plus 56 is 106, and that's what we were supposed to get. So, yeah, looks like we set things up right. And for a change, I did the arithmetic correctly. So, the answer would be x equals 56 and y equals 25. Not too bad. But they asked for x plus y, which is, you got to add 56 to the y. D1, so C. It's tempting to, I think they were hoping you'd goof and like grab 56 or 106 as you were partway through your calculations. You glance over here, you get 106, okay, 106. No. They asked for the value of x plus y. That's this one over here. So what you had to do was find x and y and then add them up. A little bit tricky, but not really a big deal. Here's a little bit tricky one, I guess, maybe. I want to know which one of these would not get used in showing that this triangle is congruent to this one here. And of course they overlap, just to make it extra complicated. Well, you would first think that base angles theorem doesn't have much to do with it, since that applies to isosceles triangles. Neither one of these appears to be that. But what about down here? Well, the intersection forms an isosceles triangle. And what do we know? We know that from the base angles theorem that these two angles are congruent. But these two angles, this is the angle in this triangle, and this angle is in this triangle, and this angle is part of this triangle. So now we have that two angles in these two triangles are congruent. If we could find one side that was congruent, we'd be all done. Well, how about this? This is 5 meters. Or this whole side would be 5 meters plus FC. This whole side would be 5 meters plus FC. Sounds like the same thing to me. So, what do we have? Two angles. This angle and this angle are congruent, and the side in between them. So, by ASA, we do know that both of them are congruent. We used our base angles theorem. We used our segment addition postulate because we added up this segment and this segment. Corresponding parts of congruent triangles are congruent. I see. I think I said it wrong. I said we were going to show that this triangle is congruent to this triangle. Well, that's part of it. We're going to do that in order to prove that these two angles are congruent. In other words, angle A and angle D. That's one way, always, to show that two angles are congruent. If they're angles in a triangle, and the triangles are congruent, then you know that if they are the corresponding angles of the congruent triangles, then they must be congruent also. So we did use our base angles theorem. We used our segment addition postulate to show that these two triangles were congruent. And to show that these two angles are congruent, we're going to use our corresponding parts of that's our CP, CTC. This, now this is a way to prove that two triangles are congruent, but we already had that. We didn't need to do anything more. We used our angle side angle for that, so This is the one we really didn't need. Wasn't that obvious, was it? Here's one where they want to know which one of these coordinates would form a triangle congruent to triangle JKL. It looks like it would take forever. You have to plot these 3 points and check out that triangle. Plot these 3 and on down the line. Maybe we can make use of what we know to begin with. What do we know? Well, the way this is drawn, it's right along the grid lines, so I think it's safe to assume that this is intended to be a right triangle. And I think it's okay for us to know that this has a side of length 2 and this has a side of length 3. So, if we could find, and notice if we could find, just spot pairs in here that would have a difference of 2 or 3 in the x or the y coordinates, we don't know what the orientation of this congruent triangle is going to be. But notice that there's a lot of similarity in they seem to lie along, like these two have the same x coordinates, so they lie along the same vertical line. These two have the same y coordinates, so they lie along the same horizontal line. In fact, this would be a good place to start. It looks to me like this one and this one are separated by 2, so one side would have a length of 2. Unfortunately, this and this, well, they'd have a length of 2 also. Not so good. Well, let's see here. This would have a difference of 3. And 2 in the x coordinates. And this would have a difference of 2. Well, we might be onto something here with this one. Let's take a look and see what happens. Well, I went ahead and sketched this in. That's for C here. Starting to look kind of good to me. Let's see, we got a 0.21 here, right? And we got 0.23 here. And 5.1 out here. So this has length, this goes from 2 to 5. So this has length 3. This one goes from 1 to 3 in the y coordinates. This has length 2. And this is a right angle in between them. Like it just follows the grids here. So, boom. Since it's a right angle, we only need to show that 2 legs are congruent, because the angle in between obviously is congruent. They're both 90 degrees. So the answer would be C. I'm not sure I really couldn't give you a quick, simple rule you would use to solve a problem like this. Just spot whatever you can in here to make life easy for yourself and see what happens. In this case, we noticed that we had nice, simple integers for the 2 legs. So I just looked for similar differences in the x and y coordinates in the points up here and got lucky and spotted this one. We tried it out and it worked. Well, this one might look a little weird to you. After all, how are we going to set up an algebraic equation? We don't have any numbers other than variables. This is one of the perimeter, right? So we got to add this and this and this and set it equal to what? Wait a minute. We've got 2 congruent angles here. And remember, the converse of our base angles theorem means that if we have 2 congruent angles, then the opposite sides are congruent, or we have an isosceles triangle. Now we got something we can work with. We can set this equation equal to this. In fact, let's do that. we can solve for x, all we have to do is put it in down here and perform our additions. Subtract 2x from each side and get x over here, add 2 to each side and get 5 over here. So if I did this right, I've got 15 minus 2 is 13 over here. I've got 10 plus 3 is 13 over here. Well, that's a step in the right direction because these were supposed to turn out to be equal. And 25 down here. So we got 26 and 25. I believe the perimeter would be 51. All you had to do was recognize that if you've got two congruent angles in a triangle, then you've got an isosceles triangle. That was the whole trick to this one. Here's one that looks kind of complicated. Yeah, it's tempting to draw the triangle, set up your grid, perform the translation and see what happens. None of that would be necessary. We have what is basically an equation which tells us exactly what any vertex is going to move into. For instance, the y-coordinate of the image, well, gee whiz. B is minus 2, 4, so minus 2 plus 8 and minus 4 minus 0.5. So the image of B is 6 comma minus 4.5. And all they asked for, in fact, was the y-coordinate. So you could have even saved yourself a little bit of time by just subtracting 0.5 from 4, and boom, you're done. All you the answer was just minus 4.5. This is just in a sense, if you recognize what this means, this problem is just an arithmetic problem. If you can add 0.5 to 4, you've got it. Now here's one that looks like they're trying to mess you up. I'm not sure that these x's actually mean anything or of any value, other than to let you, well, I guess they are, because that's what tells us we have an equilateral triangle. They could have just gone boom, boom. It could have gone like this. Same thing. The fact that it happens to be x is, near as I can tell, going to be irrelevant. The fact that it's an equilateral triangle, that's very relevant. That's the only, well, one of the few triangles. A 90-degree triangle, we know one of the angles for sure. In an equilateral triangle, we automatically know every angle. They're all 60 degrees. We proved that already. So all we have to do is write 3x plus 18 equals 60, or x plus 6 equals 20. Just divide everything by 3. I don't know why, it just seemed easier that way. Or x equals 14. Does that work? Well, I think so. 3 times 14 is 42, and 18, well, that would be 60. So, like I said, the trick to this was just recognizing we have an equilateral triangle. All the angles in an equilateral triangle are 60 degrees, so set this expression equal to 60, and you've got it. And here we have where we're given that this triangle here, ABE, this upper left triangle, is congruent to EDC, this lower right. So this is congruent to this. We need to show that EFA, that's this one here, and they're probably going to show that it's congruent to this one, right? CBE, yeah. This is congruent to this, upper left, lower right. Now we're going to show that lower left, upper right are also congruent. So what can we do here? Well, here's the right angle. And since these are right angles, we can draw the legs. This must be would say this is congruent to this side. Why? Well, this is one side of our right triangle. This is another side, and they are most definitely congruent. You can see that from the way it's drawn. So, we've got our corresponding parts are congruent. Here's the right angle in here. And I just drew these in so we can start working. We need to show that this is congruent to this. Well, we do know that this side, or pardon me, hypotenuse, is the same as this is. In other words, this hypotenuse is congruent to this hypotenuse. Why? Well, because this right triangle is congruent to this right triangle. So we put these in here, and we have that this side, in the case of a right triangle, it's called a leg. So this leg, oh, that's not relevant. We're looking for this one up here. Pardon me. We have a right triangle here. Pardon me, a right angle. How do we know it's a right angle? Well, because we got a right angle here. These things are, so we got a right, and they already tell us this is a right angle. No, they didn't tell us, but we know it is because this is drawn as a right angle. And they're congruent. In other words, this triangle is congruent to this one, so this must be a right angle because of corresponding parts of congruent triangles. Now, this is a straight angle. If one of them is a right angle, the other one has to be a right angle. We know that. So what we have when we're comparing this one to this one is the hypotenuse. I looked it up. I know mongoose is mongooses, so I'm guessing hypotenuse is hypotenuses. My dictionary didn't give a definitive answer. So I'm going to stick with hypotenuses, just because I like saying it. We know this hypotenuse is going to be congruent to this hypotenuse. So we've got a good start. This angle is congruent to this angle because they're both 90. And this leg is congruent to this leg. It's a corresponding part of this. So we know, and all we have to do is match up the hash marks. This leg is congruent to this leg. So we've got a right angle with a hypotenuse and a leg which are congruent. Right triangles only have to have, remember that's the old HL. I forget if that was a corollary or a theorem. For right triangles, all we need is a hypotenuse and a leg. And we've got that. We got a hypotenuse and a leg, hypotenuse and leg. So, boom. These two are, in fact, congruent. And it's pretty easy to see why. Here they're asking if two triangles with the same base and height are congruent. Well, it doesn't seem likely to me. After all, if they have the same base and height, what does that mean? Well, it means they'd have the same area. Is the fact that two triangles have the same area enough to make them congruent? Well, for one thing, if that were true, I think we'd have mentioned it by now, wouldn't we? If you've never heard of that, it's because it doesn't exist. There's no such thing as a theorem which says that if the areas of two triangles are equal, they're congruent, because it's not true. And we'll take a look at an example here and see why. Well, here I drew two triangles with the same base and height. You can see that they have the same height because I drew them right next to each other. Make it real easy. So we have this line here defining the height, and of course for this one we would just have this little dotted line here. You can see that they're the same. Base, well, eyeball it. I drew them the same. So the area of this is 1/2 BH. Area of this is 1/2 BH. They'll come out to be the same number, but they aren't even close to being congruent, are they? This is a right triangle. This isn't. So if we actually draw a picture, we've got our right angle down here at the bottom, and our 72 or 6 foot piece across here. Well, these are both 45 degrees, right? So that means we have an isosceles right triangle. Why? Well, if we have two congruent angles, in the case of a right triangle, they would have to be 45, because that's, we got 90 here, there's 90 left over if they're all going to add up to 180. Divide 90 by 2 and you get 45. So any triangle you construct using these directions is going to be congruent. For one thing, we have our two angles and a hypotenuse is enough to guarantee that they're congruent. And this is even easier because we know that it's an isosceles, which means we have three angles and a hypotenuse that are all congruent. If we did construct another one following the directions, we would have this. These would be 45 degrees, and this is 6 feet. So if you want to forget that it's a right triangle for the moment, we have congruent angle, congruent angle, congruent angle, congruent angle, and congruent side. So if nothing else, we have angle, side, angle to make them congruent. We could make use of the fact that it's a right triangle and find other ways to prove that they're congruent. There's lots of different ways to show that these two would have to be congruent. Side angle side's pretty quick and easy. I suppose that's what they were getting at. But generally speaking, a set of plans isn't worth much if you don't end up with exactly the same thing when you follow them. If these plans were set up, suppose that wasn't there. It didn't say 72 inches, they just left it open. Well, then you wouldn't be making congruent triangles, and as plans go, two people following the same plan could end up with completely different objects. Well, I guess they both end up with right triangles, but they'd be all different sizes. Well, this question, the way they've written it, I think they expect you to just graphically reflect this about the x-axis and then watch what happens to the coordinates, I guess. I'm more into analytical ways of doing things. They make for nice, simple rules that you can remember and never make mistakes. In this case, just use the coordinates. We want to reflect it. Well, what do we know about a reflection from the x-axis? Remember, we just know that xy goes to x minus y. Well, if we're going to eyeball a reflection, I don't see anything wrong with just eyeballing the points. So we got the point 2, 1 here, right? Over here. 4. So first I would just label the points. And I would use this. I wouldn't do it visually. It's a nice simple rule. Why not use it? So this becomes 2 minus 1. This one becomes 4 minus 5 down here somewhere. And this becomes 5 minus 3. Well, we just did that up here, right? We wrote down the coordinates of the image. What do you notice? Well, this is all kind of backwards. It's either doing this problem pretending you don't know this rule, I guess. Because what you're supposed to, we solved the problem by using the rule that they're asking us to notice. Well, we already know the rule. The rule is you flip the sign of the y coordinate. That's pretty much it. Not sure why they write it that way. I thought we already had that rule. If not, well, you've got it now. don't hesitate to use it.